Hi, and welcome to the next lecture unit in the third chapter, which is on Softmax Regression, where I will generalize the binary classifier logistic regression to the multiclass case. So remember, how was logistic regression defined? So we usually assume that we have such a 0-1 encoding of our class label going on here, and then we combined this hypothesis space of linear functions, which was transformed by this logistic function S. So we had this hypothesis space here for linear predictors going on, and we combined that with the Bernoulli or log loss, which looked like this and was defined on these estimated posterior probabilities here. And then the resulting model we simply called logistic regression, and we also showed that this is a linear classifier where the optimal decision boundary is a simple hyperplane. And for all of the notation going on in this slide set here, I will again suppress this intercept term for better readability, as I've done a couple of times now in previous lecture units. So there's a straightforward generalization now to the multiclass case. So instead of me modeling a single linear discriminant function, I now have G linear discriminant functions going on, fk of x. And because I still only want to consider linear models, I will make the assumption that these scoring functions here are again simple linear scoring functions, which are all represented by such a parameter vector theta k. So now I don't have a single p-dimensional theta parameter vector. I should probably say p plus 1, I guess, because I'm including the intercept into the parameterization. I have k of these vectors going on. And each of these functions fk for a certain x now encode or indicate the confidence in class k, and they all go from minus infinity to plus infinity. If I want to transform these scores for a certain x into posterior probabilities, I'm now not using this logistic function, I'm using the so-called softmax function, which I will also denote with an S. And the reason I'm using an S here for the softmax and for the logistic is because the softmax is a straightforward and direct generalization of this two-class case into a G-class case. So what this softmax function here does is it takes a G-dimensional score vector and transforms it into a G-dimensional scoring vector again in a rank-preserving manner through this formula here. And what happens is that I can immediately prove for softmax that first of all of these guys here lie in the interval 0-1. Yeah? So I can consider these here. Well, first of all, they all lie in the interval from 0 to 1 in this unit interval. And if I sum these guys up, I will always obtain a 1 if I sum this up over all G classes. And this is the reason why we can see these as encodings of our posterior probabilities, and that our scores, our G-dimensional score vectors are now transformed into G-dimensional probability vectors. And I can also easily prove that this formula here is a straightforward generalization of this binary logistic sigmoidal function for the class for the binary case. And if G equals 2, the softmax completely coincides with the logistic function and is equivalent to it. And instead of me using the Bernoulli loss now on such a hypothesis space, as in the binary case, I can now simply use the multiclass logarithmic loss, the multiclass log loss as introduced in the lecture unit before. And I also know that this is a straightforward generalization of this binary thing here. And again, for G equals 2, this log loss will completely coincide with the Bernoulli loss. There's another comment I should probably make for the softmax function, and that is where does that name softmax come from? So this sounds a little bit like a soft approximation of the max function, and that's actually not completely true. It's actually a soft approximation of the argmax function. So if you, for example, consider such a vector here with 3 components, and the middle component is super large compared to the other 2 guys, what would the argmax function do? The argmax function would tell you which of these guys here is the maximum, so where the maximum actually occurs. And you could write that down as 0, 1 encoding, and then it would look like this here. And this is really nearly what the softmax computes. So the softmax, especially for such an extreme case, will reduce this and this guy here nearly to 0, not exactly to 0, but nearly to 0. And this here will be very, very close to 1. So this is why this is called softmax. So it's a slight misnomer. Should probably be called soft argmax. So this is a kind of a continuous approximation of this hard discrete argmax function if you assume that your result should be 0, 1 encoded like that. And another technical comment on softmax. So softmax is actually invariant to constant offsets. So if you take any type of input here and you add a constant c, so a constant shift to all of the components, what happens is that this does not change the computed outcome, and the reason for that is because in this formula here you can always, for all of the components, draw out such an x of c term, and then you can simply cancel that out here in this fraction, and again you end up with the normal softmax formula. So here's a little comparison table for logistic regression with a softmax regression. Logistic regression, 0, 1 labels. Softmax regression, you have G classes. Probably should have noted down that they are usually also 0, 1 encoded. You have one discriminant function here for logistic regression. Here you have k discriminant functions, 1 for each class. Here you have your logistic function for turning scores, for turning these linear scores into probabilities. Here you have your softmax function going on, which turns such a g-dimensional score vector into a g-dimensional probability vector. And here you use the Bernoulli loss, and here you use the multiclass log loss. You can also, if you wanted to, schematically depict the computation in softmax regression as here these p input nodes, and then here these linear computation scoring nodes, and then at the end your softmax transformation. So this is your computation of your linear score in such a graph, and now you do the softmax computation, and what you can see from that is that you're basically using now a simple one-layer neural network for softmax regression. Based on this hypothesis-based definition plus the risk function with the multiclass log loss, you can now simply calculate gradients and optimize with standard numerical optimization software. So softmax regression has that somewhat unusual property that it kind of has a redundant set of parameters. I guess you can kind of already see that from the fact that also in the binary case, we really didn't need 2 parameter vectors theta, right? We just needed 1 for the positive class. So in the G class case, we also don't really need G theta vectors. We kind of just need G minus 1. Or another way to see this was from this technical comment here, that if I shift by such a constant, the model actually stays the same. So if I, for example, subtract a fixed vector theta k, if I subtract a fixed vector from all theta k, my predictions do not change at all. So my model is actually over-parameterized if I use g different vectors theta k here. So for any specific situation that I might want to fit, there are actually now multiple parameter vectors that give rise to exactly the same hypothesis function. This implies that the minimizer of this empirical risk here is not unique, but I can still fortunately show that even in that case, my empirical risk is convex. So I can do a simple trick to kind of well define my minimizer to a unique solution, and that is just by always defining and fixing, for example, theta g to be the zero vector and only optimize over all of the remaining theta k for k equals 1 to g minus 1. A similar approach is used actually in many different machine learning models, so multiclass, logistic, discriminant analysis, naive Bayes, neural networks, and boosting, and so on for this multiclass case. And excuse me, again, softmax regression gives us a linear classifier, which is really, really simple to see because this S function here is a rank preserving function. So all of the ranks among the scores are exactly the ranks as the computed posterior probabilities. So this guy here is actually invertible. And for that reason, we know easily and directly that all decision boundaries between two pairs of classes are geometrically represented by hyperplanes, and formally softmax regression gives us, or is contained in the class of linear classifiers. And as I said, I don't necessarily have to restrict these scoring functions here to linear functions. I only do this for softmax regression, but in general, any type of scoring hypothesis of any type of function could be represented here through my hypothesis space. And then I can still use this multi-class loss and optimize over my scoring functions and their parameters by the same principle, and then actually produce nonlinear multi-class classifiers through the same principle. And one instance where this is actually done in exactly that manner are neural networks. So here, for example, I have written down a 2-layer neural network with an intermediate layer Z and then my output layer F. So in this case, the scoring functions here are obviously nonlinear functions. If this Z guy here is also nonlinear, and it usually is because this usually contains a nonlinear activation component. And again, I would minimize such a system with respect to that multi-class log loss. And usually in these cases, it's called cross entropy. And why that term is used, I will discuss and explain in the lecture chapter on information theory.